Hello, everybody. My name is Lucio Isa, and it's a pleasure to be giving this online seminar at these conferences. And thank you very much for inviting me to give my presentation to you today. So today, what I would like to talk about is some of the recent work from our group, where we looked at how we can essentially engineer the contacts between particles in suspension to design their discontinuous shear thickening response. So in such a rheology community, I don't really have to introduce too much about what discontinuous shear thickening is, or shear thickening in general. But just very briefly, shear thickening is defined as a viscosity increase of a suspension upon increasing shear rate or shear stress. And we essentially have two different types of shear thickening that can take place. We can either have a continuous moderate increase of the viscosity, which is what we call continuous shear thickening, or we can have a divergence of the viscosity as a finite rate, which is what we call discontinuous shear thickening. And today I will be focusing on discontinuous shear thickening. In particular, in recent years, there's been a growing consensus from both experiments, simulations, and theory, which basically identify the fact that interparticle contacts are important in determining the occurrence and the severity of discontinuous shear thickening. And this importance of interparticle contacts is typically ascribed to the so-called transition between a lubrication to friction scenario. So if we think about particles that are sheared in a fluid at low shear rates or at low concentration of particles, a low volume fraction of particles, particles are well lubricated by thin fluid films such that when two particles shear past one another, dissipation occurs through the shearing of the fluid film that separates them. Instead, at either high shear or higher concentration, where the particles are sheared fast past each other, then these lubrication fluid films can break and the surface of the particles can actually enter into contact. So this means that then the rheology of our suspension is actually intimately connected to the tribology of the contact of the surfaces of the particles that are sliding past each other. And therefore, the rheology is directly coupled to how the friction coefficient between the surface of the particle changes as a function of the normal load and as a function of the speed of the sliding speed at contact. So this is described by such a graph, typically in tribology, that is called the Streiberg curve, which basically divides region of high shear and high velocity and high viscosity of fluids in contact, where dissipation is dominated by hydrodynamic lubrication in this thin fluid film, to the case of either high load, where the surfaces of the particles break through the liquid fluid film and get into direct contact, and where the boundary lubrication, so contact friction between the two surfaces, become important. And in particular, because boundary lubrication becomes important, then there are specific aspects of the interparticle contacts that can be tuned to tune discontinuous shear thickening. So for instance, one can tune surface topography, and in particular surface roughness, and it's been demonstrated by us and others that surface roughness is a strong implication on shear thickening. One can tune directly the friction between the surfaces, for instance, by having lubricious polymers or different friction coefficients attached onto the sliding surfaces. Or this is also connected to the presence of adhesion between the surfaces that can, again, be controlled and designed by looking at the surface chemistries of the two surfaces in relative motion. So essentially, there is a link between the contact properties of the particles through topography, friction, and adhesion, and the macroscopic rheological response of the discontinuous shear thickening systems once particles break through these hydrodynamic lubrication films and they actually get into contact. And so what I would like to do with you today in this talk is to tell you basically how in our group we start from the design of model colloidal systems, of which we can control the contact properties, the topography, the adhesion, and the friction, and then show you how by controlling those, we can control both the macroscopic rheological response, but connect this macroscopic rheological response to the single particle contact properties that we characterize by means of atomic force microscopy, both in terms of adhesion and friction. So let's start with the design of the experimental colloidal model systems. So we start with particles that we call raspberry particles for reasons that will become apparent to you in a moment. So these are silica-based systems where we take a large core particle of silica and then modify the surface charge by absorbing positively charged polyelectrolytes. And then we decorate that positively charged silica surface by negatively charged silica nanoparticles to produce what we call the native raspberry particle. Then onto these particles over here, we grow through a Stover synthesis process, we grow a second layer of silica that actually smoothens the surface of the silica particle and has both the property of, let's say, mechanically anchoring in a strong way these individual asperities onto the surface of the particle, as well as providing additional control onto the surface roughness. So if we do this, then we can produce different kinds of rough particles, from smooth, let's say, native silica cores all the way to varying roughnesses. And we characterize the roughness of these particles by means of atomic force microscopy. And in particular, we identify for each of these surfaces, we identify the average height and the average distance between asperities. And we rank surface roughness basically by the values of a dimensionless roughness parameter, which is given by the ratio of the average asperity height divided by the average interasperity distance. And if we do this, we can have surfaces that have different values of these h over d parameters, from approximately 0 for the case of smooth particles, all the way, let's say, up to about 0.5 for the roughest particles that we have produced for this study. After that, we can also change not just the topography, but both the friction and the adhesion of these particles by growing well-defined polymer brushes onto the surface of the silica particles. And in particular, in this study, what I'm going to show you is that we can grow polynipalm brushes, where polynipalm is a thermoresponsive polymer that can swell and deswell by crossing a critical temperature that is approximately around 32 degrees. And by doing so, we can change both the effective particle size, but also the effective interparticle contact interactions by means of changing adhesion and friction. So in particular, what we do here is that we start with smooth particles or with raspberry particles, and by means of surface-initiated ATRP, we can grow polynipalm brushes onto the surfaces, where at 20 degrees, these polynipalm brushes will be swollen, while at 40 degrees, these polynipalm brushes will be collapsed. And basically, by changing the thickness of the polynipalm brushes at the various temperatures, and by changing and by varying the thickness of the polynipalm brushes relative to the roughness of the underlying features, we can then have a library of particles of which we can selectively turn on and off both adhesion and friction, and as I will show you in a moment. In particular, this refined polymerization strategy really allows us to control the thickness of the polynipalm brushes, both in the swollen and deswollen state, over different particle roughnesses, different particle topographies. So let's just start now with the characterization of the rheological response of these systems. We will start with silica particles that have no polymer onto the surface. And we first start by examining the influence that surface roughness has on phi m, which is defined as the maximum frictional packing fraction where you sediment. Basically, this indicates the maximum packing fraction at which you can process your suspension at high shear. And we identify and measure this quantity by using a simple sedimentation experiment where we fill capillaries with a dilute suspension of particles, and we spin that down at high rate, and we measure the height of the sediment. And then if we measure the height of the sediment relative to the initial height of the liquid column, then this directly gives us the packing fraction of the sediment, which we can extract very precisely by changing the initial volume fraction of the particles in the capillary, such that essentially the slope of this line basically tells us what this maximum packing fraction is. And what we find in this system, as it had been found by others, is that if we make the system rougher and rougher, basically this maximum packing fraction decreases. So the rougher the particles are, the easier it is for them to jam during sedimentation, such that the sediment gets looser and looser as we increase particle surface roughness. So this has the implication that the rougher the surface of the particles, the lower is the maximum packing fraction at which they can be processed. And if we do that, then we can, for instance, look at the overall response of these suspensions upon an impact experiment, where we see that for smooth particles, the value of phi m is of the order of 59%, such that if we are significantly below phi m, the system behaves essentially as a shear thinning fluid. But as we approach phi m, then the system actually becomes discontinuously shear thickening, and you see solidification upon impact. If we now go for the roughest particles that we have looked at, the increase in surface roughness causes a decrease of the maximum packing fraction of about 15%. And qualitatively, we see the same response that we saw before for the smooth particles, only significantly anticipating in terms of values of packing fraction. But the question is just not that. I mean, this is the response that we have for the system is not just simply rescaled by the maximum packing fraction. We also see qualitative differences in the response. In particular, for the smooth particles, we have this, the usual transition between a continuous to a discontinuous thickening response if we increase the volume fraction of the suspension approaching phi m, while for the rough particles, there is no discernible continuous shear thickening in the system. And as soon as the particle break in the lubrication, fluid lubrication films that come into contact, immediately we have discontinuous thickening, which happens earlier and earlier if we increase the volume fraction. This is compatible with a scenario where we go from sliding particles together to the possibility of asperities onto the surface of the particles to interlock as the particles are sheared past one another. And if we now increase the overall surface roughness by keeping the volume fraction constant, then we see that higher surface roughness implicates earlier and earlier onset of discontinuous thickening. So we characterize this interlocking of particle asperities by means of atomic force microscopy. In particular, we take a single colloidal particle identical to the ones in the suspension, attach it to an AFM cantilever, and slide this onto a surface that mimics basically a counter surface with the same asperities. And what we see is that we have an increase or an effective friction coefficient if we increase the surface roughness of the surface, which corresponds to the fact that as we encounter asperities onto the surface, the friction coefficient, the friction loop measured in these experiments, shows up with the appearance of these spikes, which are corresponding to the presence of 6 slip events associated to the interlocking of asperities. So what we did here by means of atomic force microscopy is we characterized the friction coefficient of many different pairs of surfaces with different roughness of the particle as well as roughness of the substrate. And what we find is that for the symmetric condition, we have an effective friction coefficient increases as a function of an increase of this dimensionless roughness parameter h over d, such that now we can correlate these two quantities and basically plot an effective friction coefficient versus phi m. And what we see is that if we increase the effective friction coefficient, then our maximum packing fraction moves further and further away from random close packing. So basically, this tells us that by engineering surface topography, we engineer the rheology of the system. Very briefly, we also showed more recently that by using particles with a thermoresponsive polymer brush, we can switch off adhesion at low temperature when the polymer brush is solvated and turn it on at high temperature when the polymer brush is then collapsed. In particular, by normal force atomic microscopy measurements, we find the onset of adhesion at high temperature caused by the hydrophobic interactions between the polynitron brushes. That is also coupled to an increase of effective friction, where at high temperature, the rough particles show systematically a higher friction coefficient compared to the particles that are coated by a fully swollen brush, which is also reflected by the fact that at high temperature, then the asperities are no longer masked by the swollen polymer brush that causes steric hindrance at contact between the particles and helps lubricating the contact. So once the polymer brush is collapsed, we actually see the asperities again. And in addition to that, now we have an additional component of dissipation which comes from adhesion. In response to that, then we have a temperature-dependent friction coefficient, such that we have then a dependence of the surface roughness on this maximum packing fraction at different temperatures. In particular, what we see is that as we increase basically the temperature, then we recover the similar behavior as I showed before, where the onset of discontinuous thickening takes place earlier and earlier, the greater is surface roughness and the greater is the relative distance basically from the maximum packing fraction. And so here, as I said, rougher particles show an earlier onset of discontinuous shear thickening, and the closer we get to the maximum packing fraction, the earlier the system starts to exhibit discontinuous thickening. So roughness coupled to adhesion essentially leads to an increase in frictional force, which then gives rise to an increased discontinuous shear thickening. Before finishing, I just want to very briefly show you that these elements that we have described now are of direct importance in terms of processing of suspensions. In particular, what we've demonstrated is that if we mix together two different particle types with two different surface roughnesses, very quickly it is sufficient to have a small number of smooth particles to disrupt these force chains of particles that have interlocking contacts, such that the maximum packing fraction of a suspension that only has 5% of smooth particles is significantly larger than the ones of the purely rough suspension. As a consequence of that, we have that by simply mixing in 5% of smooth particles in a suspension that has 95% of rough particles, we can delay the onset of shear thickening by 2 orders of magnitude. And similar results have been also observed by recent work by others. To finish, by looking at these thermoresponsive systems, because by increasing basically temperature, we can switch on friction and adhesion. The consequence of that is that depending on at which shear rate we measure the viscosity of the sample, if we are at a shear rate that is below the critical shear rate for the onset of discontinuous thickening, the swollen particles at 20 degrees have a higher viscosity just because their effective volume fraction is greater. And the same thing is if we measure again at 1 inverse second, which is below the critical rate for the onset of thickening. But if we go above that rate, then all of a sudden, the particles with the collapsed polymer brush that have a lower effective hydrodynamic volume fraction show an increased viscosity, because now we switch on basically the contact interaction in terms of adhesion and friction, which then gives us a higher viscosity. So with that, we can demonstrate that we can engineer contacts essentially to engineer rheology. So this brings me to the end of this presentation. I would like to thank the people that have contributed to this work, in particular Nick Spencer, Chao-Peng Xu, Shivar Prakash Ramakrishna, and Joydeb Mandal, who have contributed to various aspects of this work, and ETH Zurich for funding. And thank you very much for your attention.